Welcome back to elementary statistics. Now that we've spent some time getting familiar with the standard deviation formula, in this video I want to go through a couple of applications that use standard deviation. Before I do that though, a quick refresher. If I get my head out of the way, we talked previously about the standard deviation, and when we did, we separately discussed population parameters, where we had the mean represented using the Greek letter mu, and the standard deviation represented using the Greek letter sigma with the formula square root of the sum of x minus mu squared all over n, where n is the number of members of the population. We also talked about sample statistics, where we had the mean represented by x bar and the standard deviation represented by s, given by the square root of the sum of x minus x bar squared all over n minus 1. And I talked a little bit about why that difference occurs in the video on using these formulas in general. What I want to point out here is that in this video, I'm going to go through several formulas. I'm going to talk about how you can use the population mean and standard deviation, and then I'm going to show you the exact same formula using the sample mean and standard deviation. Before I do that, I did want to stress that just because we use this slightly different formula, that's not the end of the story. I really want you, as part of this lesson, to start getting accustomed to using the Greek letters to represent population parameters, using the English alphabet Roman characters to represent things, the statistics on a sample. Because moving forward, we're going to hit the point where we're looking at complicated things and we are comparing sets of samples, right? That's not going to happen now, but a couple of weeks down the road, where the population and the sample, right? Population mean and sample mean, population standard deviation and sample standard deviation are both going to appear in the same formula. So with that eye to the future in mind, it's not just I'm repeating myself for the sake of repeating myself. It is important to understand the difference between the variables for the population parameters and the sample statistics. This lesson on its face doesn't show you that as much as I would like it to. And I want you to keep that in mind as you go through the rest of this lesson. This is something that you want to practice now so that when it comes up and everything is going on at the same time, it's less confusing then. All right. So standard deviation is a measure of dispersion, which is a fancy way of saying how spread out are the data in a distribution. All right. Thinking about normally distributed data, and again, I'm getting ahead of myself, but in the future, we're going to be seeing things where normally distributed data is going to come up a lot more than it feels like it should with what we've talked about so far. But if you think about normally distributed data, which has a frequency curve that looks something like that, I can change this distribution around a little bit And I can make it very tall and skinny. And it's still the same basic shape. I've just stretched it in one direction and shrunk it in another. This tall and skinny distribution has most of the data points relatively close together. So it has a relatively small standard deviation. And I can also try to take things in the other direction. Let's try to make that horizontal axis a little closer to horizontal and draw this as a very wide and rather short distribution. And in this case, the data points are quite a bit more spread out. This distribution has a larger standard deviation, and then the first one I drew is somewhere more in the middle. Trying to quantify that a little bit takes us to the range rule of thumb. Remember that the range of a distribution is largest value in the distribution minus the smallest value in the distribution. So how far is it from the smallest point to the largest point? That's the range of the distribution. The range rule of thumb tells us that the range is approximately 4 times the standard deviation. All right, that's true for a population, and that's true for a sample either way. The range is approximately 4 times the standard deviation. All right, I'm using just a tilde here for approximately. I'm not even using the approximately equal that you see more often in algebra courses, because this very much is a rule of thumb. The problem with talking about range that I mentioned previously is outliers are a real issue. If you have particularly high outliers or particularly low outliers, anything that talks about the range is going to be broken. But if you have some way of ignoring outliers, and we'll talk about a couple of ways that you can mostly ignore outliers in the future, if you have a fairly well-behaved distribution, you can ignore outliers, or you don't have many outliers. At that point, this comes closer and closer to being true. The range of a distribution is about 4 times the standard deviation. All right, so there's one step in the right direction. We can actually get a little bit more specific than that. Let me redraw a nice normal distribution, and I'm going to draw this particularly large because I have to write all over it. All right, there's a nice normal distribution. One of the things we know about the normal distribution is that the center point is the mean, x bar for a sample, mu for a population. And the characteristic that makes something a normal distribution is that the mean, the median, and the mode are all at this point. But for discussions involving standard deviation, the mean is the one that's important. And what I want to do is divide my distribution up into evenly spaced on the horizontal axis, with each space being a distance of the standard deviation. So there's one standard deviation, there's a second standard deviation, and sure, there's a third standard deviation. And I'll do the same thing going in the other direction. So there's one standard deviation, there's two standard deviations, and there's three standard deviations. All right, so if I'm moving by steps of a standard deviation, if the center point is the mean, then we have the mean plus one standard deviation. We have the mean plus two standard deviations. And we have the mean plus three standard deviations. All right, I'm running out of space. I'm not going to try to label this using both the population and the sample. Population parameters are going to be good enough for giving us enough space to label these things. Going the other way, we have the mean minus a standard deviation. We have the mean minus 2 times the standard deviation. And we have the mean minus 3 times the standard deviation. That's literally what it means to take a step the size of the standard deviation. Just add or subtract the standard deviation from the previous place you were. All right, I'm running out of colors here. All right. The next thing up, I want to talk about the empirical rule, which is one of probably the worst phrased things in statistics, but it is a very valuable tool. The empirical rule says that if you take this part of the distribution, the part that is within one standard deviation of the mean, about 68% of the data in the distribution falls into that range, what I've shaded here in red. If you go 2 standard deviations in both directions, so that's all of this that I have circled in blue, in this part of the distribution, you're going to find 95% of the population. And notice here that the range on this is 4 times the standard deviation. So there's where the range rule of thumb comes in. The range rule of thumb is that, well, there's 95% of the distribution there, and ignoring a couple of weird outliers, 95% of the distribution is basically the whole distribution. Things that are further away than that are generally the things that we call outliers. And then the last thing, if I go all the way out 3 standard deviations, all of that space, that is going to be 99.7% of the distribution. Going beyond that is an extreme outlier. All right, that's what, 3 out of 1,000 points are beyond that range. All right, these 3 values, 68% within 1 standard deviation of a mean, 95% within 2 standard deviations of a mean, 99.7% within 3 standard deviations of a mean. This is the empirical rule. And using the empirical rule, building off of the empirical rule, is a lot of the use of standard deviations. My field of research interest is in physics, and in physics, 99.7% is actually not good enough for us. But we will refer to 99.7% accuracy as 3 sigmas. If we go out 1 more standard deviation, we call it 4 sigma accuracy. If we go out further, it's 5 sigma accuracy. So it's a way of describing how certain are you that you have gotten everything. And if you find a whole bunch of outliers, when you are this certain that you've gotten everything, things are strange, and strange things are the things that scientists get excited about. All right. So there's one powerful use of the standard deviation is just a way of describing what's happening to a distribution in general. Another thing that we can do is talk about relative position using the z-score. Once you stop and think about what's happening here, the idea behind relative position becomes a lot more apparent. How do you compare scores in different distributions that use different scales? As an example, let's say that a student wants to compare her results on a couple of exams to her classmates. She takes a statistics exam. Her score on the statistics exam is 97 out of 110 points. And the instructor for the statistics course publishes statistics on the exams and says that I'm writing the wrong symbol, the mean score on the exam was a 92 and the standard deviation was 9.5. This student in the same week also took a psychology test. And on the psychology test, she scored 72 out of 80. The psychology professor publishes statistics on the exam and said that the mean on this exam was a 68 and the standard deviation was 4.7. Immediately, one of the things that you might want to do is just calculate a percent, right? What percent of the exam did this particular student get right? But in a sense, that's not really fair because the grading scales in these classes might be different, right? It doesn't have to be straight percentage scales. So the more interesting question, the thing that I want to answer is, compared to the rest of the class, did the student perform better in statistics or in psychology? Compared to the student's classmates, where was she better? All right. And that is a tool that the z-score is designed for. The z-score goes back to what I was just talking about. We measure where you are in terms of standard deviations away from the mean. The formula doesn't make much sense at first, but as we get into it, it should make a lot of sense. The z-score for a population is your particular score x minus the mean divided by the standard deviation. That's the way that the z-score formula is always presented, and that's the formula that we're going to need here. But if I do a little bit of algebraic manipulation on this formula, I can rewrite that, solving for x, as x equals sigma times z plus mu. And I think this makes it a little bit more clear what's happening. My score x starts at the mean and moves some multiple of the standard deviation away from the mean. If I scroll back up to my chart, that's exactly what I was talking about here. From the mean, I move in terms of multiples of a standard deviation. So this point is the z equals 1 point. This is the z equals 2 point, and somewhere between is something in between, right? 1.3, 2.7, negative 0.5. Points in the middle are points in the middle. And we can make that continuous, and we call that a z-score. Right. This version for a population is what we need for this problem. So that I don't forget, I'm going to go ahead and write down that if we had a sample, we could do the exact same thing. X minus x bar. Why am I here? I don't want to be here. X minus x bar over s works just as well. All right, so if we had a sample, we could use that. We have a population. We're using the one that I have in a box. All right. For statistics, I'm going to call this z sub s for the z-score for statistics. This student's score was a 97. The mean was a 92, and the standard deviation was 9.5. If I punch that into my calculator, I get something on the ballpark of 0.526. Then I'll do the same thing for psychology. ZP, this student's score was a 72, the mean was a 68, and the standard deviation was a 4.7. If I punched that into my calculator, I get something in the ballpark of 0.851. And so, because the z-score here is the larger value, that tells us that the student in question performed higher compared to her classmates, compared to the average in psychology than in statistics. And if we look a little bit more closely, we can start to interpret that. One of the things that sticks out to me about this is the difference in the standard deviations. In the statistics exam, we had a fairly high standard deviation. Scores were very spread out. On the psychology exam, we had a relatively lower standard deviation. Scores were more closely packed together. So even though our student scored 5 points above average on the statistics exam and only 4 points above the average on the psychology test, because the scores were more closely packed together, a lot more students scored less than that 4 points above the average. And so we can compare these scores, even though the scoring schemes, the design of the course is very different, right? If you calculate straight percentages, the statistics exam, actually the student performed relatively poorly. I dropped my calculator as soon as I'm going to reference it. Right, a 97 out of 110 is an 88%. A 72 out of 80 is a 90%. So the student scored high B, low A, but in both cases, a pretty good ways above the average. And that's kind of the point, right? If the grading scales are different, if the grading schemes are different, weightings are different, exams mean different things, so comparing just raw scores makes absolutely no sense. Comparing the z-scores gives us more information about how the class is doing and how this particular student is doing compared to the rest of the class. All right. Another place where this sort of thing comes up is in standardized testing. The SAT math portion is a standardized test that has a mean score of 500 and a standard deviation of 100. To be clear, that doesn't mean that whenever students take the tests, this just always happens that way. This is actually engineered. What the college boards does, and what any standardized test does, is they sample a test. Before a test is given out in mass, a small sample of people take this version of the test, and the administrating body, the college boards in this case, analyzes the test. They find the mean and the standard deviation of that group. Then, when they are looking at the scores on this test, we're going to compare to that mean and standard deviation. We will find the z-score for your performance on the test compared to that population, the same way we did in the previous example, so I'm not going to take the time to do that again. So, you have a z-score. Let's say that you scored a z-score of negative 0.12. And then, we know your z-score. We know that we want the SAT math to have a mean of 500 and a standard deviation of 100. And so, we set that up. Z equals x minus mu over sigma. We can plug in our values. We can solve from there. And I get that x is 488. From here, the college boards for SATs usually rounds to the nearest 10. So we would round this and call it 490 as your SAT math portion score given your z-score. Right. The SAT, the ACT, IQ tests, anything that is called a standardized test has a scoring that is set up in this way, in some way, shape, or form. And that's how we interpret those. All right. One last thing. With the z-score, we are now able to compare one person's score in one distribution to one person's score in a different distribution. And we're going to use the z-score quite a bit moving forward in the course. But before we do move forward, another thing that you might be interested in is comparing the standard deviations themselves. How do you compare how spread out one distribution is compared to another? If the distributions use a similar scale, then it's easy, right? Think about this in terms of units. If you're measuring how far somebody is able to throw a frisbee and you measure it in feet, you can compare feet to feet to feet all day without issue. If you are trying to compare results in the United States, where frisbee throws are measured in feet, to results in Germany, where frisbee throws are measured in meters, you have to perform a unit conversion to get there. The same thing can be generalized here in our discussion of standard deviations. That generalization is called the coefficient of variation, or CVAR. Right. The coefficient of variation is the standard deviation of the population divided by the mean times 100. You can do that for a population. You can also do that for a sample. So, as a quick example, if I have one sample measured in yards, x bar, the mean of the sample is 27 feet, and the standard deviation is 5.0 feet, and I have a second sample, x bar is 7.5 yards, and the standard deviation is 1.8 yards, then by calculating the coefficient of variation for these two situations, I can get a better understanding of which one is more variable, which distribution has closely packed results, which distribution has widespread results. So CVAR, again, standard deviation divided by mean times 100. I don't need units because feet divided by feet is unitless. But my calculator is trying to fight with me. My calculator tells me that in the first case, the coefficient of variation is 18.5. And in the second case, if my calculator will stop fighting with me, I can put a number down. I get that the coefficient of variation in this case is 1.8 over 7.5 times 100, which comes out as 24. So, we can say that the first distribution has a narrower dispersion, the second distribution has a wider dispersion. Thinking about those graphs that we drew at the beginning of this lesson, this is going to be the one that looks more like that. This is going to be the one that looks more like that. In this particular case, the numbers are fairly near each other, so the graphs I drew are exaggerated, but it's the same basic idea. All right. With that, I think that's plenty enough for this lesson. Thanks as always for joining me. I'll wrap up here, and I'll see you next time.